Welcome to the deep dive. Today we're venturing into the heart of stellar nurseries. We're going to explore OB associations, these sprawling families of young, incredibly hot O and B stars that really dominate the light we see from galaxies.
Yeah, and we've got some recent discoveries that have, frankly, flipped the script a bit on how we thought these prominent stellar groupings form and, evolve over time.
That's right. The conventional wisdom for a long time was that stars are born sort of huddled together, right,
Yeah.
in dense molecular gas clouds.
Often forming these tight-knit clusters and associations. And that leads straight to some key questions we need to tackle.
Like what?
Well, first, what exactly makes a compact cluster different from a more spread out association? Are they fundamentally different beasts or just different stages?
Okay.
And second, is it really a hard rule that all stars begin their lives packed into a cluster, only to, drift apart later into these looser groups?
Exactly, and that's really where the Gaia mission just bursts onto the scene. It's delivered a bit of a cosmic curveball, hasn't it?
Oh, absolutely. This space observatory, Gaia, it's given us just astoundingly precise measurements of stars, their positions, their movements across huge distances.
And as we're about to dig into, Gaia's observations are, well, they're seriously challenging some of those deeply ingrained ideas about these stellar families.
So yeah, our mission today is to unpack these cutting-edge insights, especially the ones coming from Gaia. We want to reveal a much more nuanced picture of how these dynamic stellar nurseries are born and how they evolve.
Think of this as your fast track, your shortcut,
Yeah.
to getting up to speed on this really exciting frontier in astrophysics.
Okay, let's get started. To really understand this, we need to be clear on the terms we're using. What is an association versus a cluster?
Good point. It was a really influential study, Lada and Lada back in '91, that kind of set the standard definitions.
Right, they defined both open clusters and associations as groups of stars that, share a common origin and have a noticeably higher surface density than the background stars of the same type around them.
But they drew a distinction.
They did. Open clusters, they defined as physically related groups, usually 10 or more stars. And the key thing is their density. It's higher, around 1 solar mass per cubic parsec.
Which sounds low, but in space terms.
It's actually pretty dense, enough for gravity to hold them together against the galaxy's tides, at least for a while. They're typically maybe 1 to 10 parsecs across. That's roughly 3 to 30 light years.
Okay, so these are the tighter, more gravitationally resilient families.
Got it.
Now, what about the OB associations? How do they stack up?
Well, OB associations are also groups of, say, 10 or more related stars, but the big difference is their density. It's significantly lower, way below the limit needed for gravity to keep them stable.
So they're much more spread out.
Much more. They can be huge, tens or even hundreds of parsecs across. And because they're not tightly bound, they don't last as long as recognizable groups, maybe only 25 million years or so.
And they're identified by?
Often by that overdensity of those really luminous hot O and B stars.
Right, because those big, bright stars burn out so fast, cosmically speaking, their presence basically screams, recent star formation happened here.
Exactly. It's a dead giveaway. And we should probably quickly mention moving groups, too.
Ah, yes. What are they?
They're generally thought to be the scattered leftovers, the dispersed remnants of clusters or associations that have sort of dissolved over time.
Okay, definition set. Now let's talk about that traditional model you mentioned earlier, the monolithic formation scenario.
Right. This idea basically proposed that pretty much all stars, or at least the vast majority, are born inside these tightly packed, gravitationally bound clusters.
Okay, simple enough starting point. But if that's true, what does it imply for the OB associations we actually see, which, as you just said, aren't gravitationally bound?
Well, the necessary conclusion then is that these unbound associations must have started out as much more compact clusters. They couldn't have formed as they are.
So how did they get from compact cluster to spread out association in that model?
The proposed mechanism was gas expulsion. The idea was that after the stars form, there's still a lot of gas left over in the cluster. The powerful winds and radiation from the young, massive stars inside would then blow this remaining gas away.
And losing all that gas mass weakens the cluster's gravity.
Precisely. The gravitational glue holding the stars together weakens, and the whole cluster starts to expand, eventually becoming the large, unbound association we observe.
That sounds neat.
Uh,
Logical even. A nice, tidy story. But you hinted earlier this picture has run into some trouble.
It has, yeah. Over the last decade or so, observations of current star formation, looking at how stars are actually being born right now, have shown us a more complicated reality.
How so?
We're seeing stars forming in a much wider range of environments than just dense clusters.
Yeah.
We see them forming in these large, sprawling, hierarchical structures, sort of clumpy filaments within giant molecular clouds.
And not just in groups.
Right, and even as seemingly isolated young stars or very small groups, it's not all happening in dense clusters.
Which raises a pretty big question then.
Exactly. If stars form in all these diverse ways now, why should we assume that in the past, nearly all stars began life squashed together in tight clusters? Maybe that monolithic starting point wasn't so universal.
And this is where Gaia steps in to provide some actual data on the motions, right? To test this expansion idea.
Precisely. A major goal for Gaia was to find and study these associations far beyond what we could before, out to maybe 2,000 parsecs, or over 6,000 light years, and crucially identify even the fainter, lower mass stars that belong to them.
So what did the early Gaia data start to show? Did it support the expansion idea?
Well, interestingly, no. The very first studies using Gaia data started to hint at a mismatch with that monolithic, gas expulsion-driven expansion scenario.
Really? What were the mismatch?
The big surprise was that when they looked at the velocities of the stars within these associations, they didn't see much evidence for the kind of systematic, large-scale expansion you'd expect if they were exploded clusters.
Huh. So they weren't all flying outwards from a central point, as the theory predicted.
Generally, no. Their overall motion seemed more randomized, not the clear signature of a past explosion or rapid expansion.
Okay, that is a challenge to the old model. Were there specific studies finding this?
Yeah, a few key ones early on. Melnick and Dambis in 2017 looked at 18 nearby OB associations using Gaia's first data release, DR1, found very little sign of systematic expansion.
All right.
Then Ward and colleagues in 2018 looked at another 18 associations, also using DR1, came to pretty much the same conclusion. No strong expansion signature.
Wow. Any others?
And Wright and Momajek, also using Gaia DR1, studied Scorpius Centaurus. That's one of our closest and best studied associations. They suggested it probably didn't form in one single burst.
What did they suggest instead?
They argued it likely formed with a lot of internal substructure already present, maybe through multiple smaller episodes of star formation spread out a bit, not one big monolithic event that then expanded.
Okay, so these early results were already casting doubt. Did this trend continue as more Gaia data came out?
It did, largely. Melnick and Dambis followed up in 2020, using the richer Gaia DR2 dataset. They looked at 28 associations, and again found that most of them just weren't expanding in that simple, expected way.
Most of them. Were there any exceptions?
Well, there was one interesting case, Vela OB2. A study by Cantat Godin and others in 2019 did find evidence of expansion there.
Ah, so maybe the model works sometimes.
Not so fast. Even in Vela OB2, the Gaia data suggested the expansion probably started before most of the stars we see there even formed.
Before? How does that work?
The idea is that the expansion might have been triggered by something else, like the shockwave from a nearby supernova explosion that compressed gas and then triggered the star formation within that already expanding bubble. So the star formation didn't drive the expansion. It happened within an expanding structure.
I see. So even the potential counterexample doesn't really fit the standard gas expulsion model. The expansion came first.
Exactly. So the overall evidence for that simple expansion model driven by gas expulsion was looking pretty weak by this point.
Okay, so that leads us to this more comprehensive study you mentioned by Ward and colleagues again. But using the Gaia DR2 data in 2020, sounds like a big one.
It really was a major effort. They started with a huge catalog, Galeb stars, which had something like 16,000 OB star candidates.
Wow.
Then they used Gaia's super precise color data to clean up that sample, ending up with nearly 12,000 reliable OB stars stretching way out, 3,000 or 4,000 parsecs away. That's, 10,000 light years or more.
That's an incredible data set. What did they do with all those stars? Did they just map them?
Well, mapping was the first step. Interestingly, when they first plotted them, the associations looked sort of stretched out along our line of sight, radially.
Like cigars pointing towards us?
Kind of, yeah. But they figured out this was mostly an artifact caused by the remaining uncertainties in the distance measurements, even with Gaia.
Ah, okay. So they corrected for that.
They used a sophisticated cluster finding algorithm, basically letting the computer group the stars based on their positions and velocities in 3D space. And that led them to identify a whopping 109 distinct OB associations out to about 3,000 parsecs.
109. That's way more than were known before, right?
Oh, absolutely. And these typically contain maybe 10 to 50 of those bright OB stars each, but then they went further.
Oh.
They searched the full Gaia dataset for fainter, lower mass stars that seem to be moving along with each of these 109 associations, and they found thousands, on average about 6,000 stars per association.
Good grief. 6,000 stars per group. That gives you a lot of kinematic information to work with. So what did they analyze?
Exactly. Their main focus was the kinematics. How are all these stars moving within each association? They looked at things like velocity dispersion, the spread in velocities,
Okay.
and crucially, they tried to quantify if there was any significant expansion happening beyond just the random motions you'd expect from individual stars buzzing around.
And the verdict. Did they find the expansion signature this time with all that data?
Nope. Their main conclusion was pretty definitive. That simple picture monolithic cluster forms, expels gas, expands uniformly. That scenario is basically ruled out as the main way OB associations form.
Ruled out. Okay. But what did they find? Was it just totally random motion then?
Interestingly, no, not purely random either. The data was also inconsistent with just a completely chaotic, unstructured velocity field. It wasn't simple expansion, but it wasn't pure randomness either.
So, uh, somewhere in between. What could explain that?
They propose a more complex, more nuanced picture. Their explanation is that you need a combination of things.
Such as?
First, small-scale, localized expansion events happening within smaller clumps or substructures inside the larger association. Imagine little pockets puffing outward slightly, but not the whole thing blowing up uniformly.
Okay, localized expansion. What else?
Second, positional substructure. The stars aren't smoothly distributed, they're clumpy. And third, a velocity field that, while generally randomized, still has some underlying structure related to those clumps. It's not perfectly smooth.
So internal clumps, localized puffing within those clumps, and an overall motion that's messy but not totally random.
That's the idea. And that combination, they found, could actually reproduce the kind of kinematic properties they were observing in the Gaia data much better than the simple expansion model or pure randomness.
Okay, Gaia is really pushing us to rethink this from the ground up. What does this all mean for the bigger picture of star formation theory?
Well, the big implication is that Gaia provides really compelling evidence against those simple expansion models, and by extension, against the idea that most stars must form in clusters that later get unbound by gas expulsion.
So what picture is consistent with the Gaia data then?
The results seem to align much better with what's called a scale-free hierarchical model of star formation.
Scale-free and hierarchical. Okay, unpack that for us. What does that mean in practice?
It means thinking about star formation not as something that only happens in these special dense cluster environments. Instead, stars form across a whole continuous range of densities within the giant molecular clouds.
So not just in the dense knots, but all through the cloud structure.
Pretty much. Think of the cloud as this big, clumpy, filamentary thing. Stars can form in the really dense clumps, sure, maybe leading to bound clusters sometimes, but they can also form in less dense regions, in looser configurations, maybe strung out along filaments. It's not an either, it's a spectrum.
Less like making distinct cookies, more like baking a lumpy cake where stars form everywhere.
That's actually not a bad analogy, and in this view, OB associations likely form in situ.
In situ, meaning
Meaning they form largely as they are relatively spread out, gravitationally unbound directly from these large-scale structures within the molecular clouds, rather than starting as compact clusters that then expanded.
ah, I see. So they were basically born large and somewhat loose to begin with.
That seems to be the emerging picture. Now, those localized expansion events within substructures are still likely happening and are important for the detailed motions, but they aren't the primary driver shaping the entire association from a tiny cluster.
So it's a fundamental shift from born tight, then exploded, to born widespread within a complex cloud.
Yeah.
That really changes how we visualize these stellar nurseries.
It really does, and it's worth remembering we have examples of these associations practically in our backyard, cosmically speaking,
Yeah.
within about 150 parsecs, so maybe 500 light years.
Which ones are nearby?
Well, the most famous is probably Scorpius Centaurus. It's huge on the sky and actually made of several subgroups like Lower Centaurus Crux and Upper Scorpius. Then there's Taurus Auriga, Hercules Lyra. These are our neighbors.
And didn't you mention before that even some very familiar star patterns are part of these?
Absolutely. The Ursa Major Association is a great example. Almost All the bright stars in the Plough, or the Big Dipper as it's known in North America, all except the two end stars, Duhe and Alkaid. They're all moving together as part of this association.
Wow. So the Big Dipper is mostly a dissolving star family.
In essence, yes, a moving group, likely the remnant of a slightly denser configuration ages ago. And we see these things elsewhere too. OB associations are found all over the Large Magellanic Cloud, our neighbor galaxy, and in Andromeda. They seem to be a standard feature of star formation in galaxies.
It's amazing they're so common, yet understanding their origins has been tricky. You mentioned Gaia was crucial. So what are the big challenges before Gaia? Why was it so hard to study them?
The main problem was their sheer size on the sky. They can cover huge patches. And because they're relatively sparse compared to dense clusters, picking out the actual members from unrelated foreground and background stars that just happen to lie along the same line of sight was incredibly difficult.
You needed to know how they were moving, right, to confirm they belong together.
Exactly. You need precise measurements of their proper motions, how they move across the sky, and their radial velocities, how they move towards or away from us. And getting that accurately for thousands of stars over large areas was tough.
Did we have any kinematic data before Gaia?
Oh, yes. The Hipparcos satellite in the 90s was a huge step forward. A study by Dezou and colleagues in 99 used Hipparcos data to make a census of associations within about a kiloparsec, roughly 3,000 light years. That really improved things for about 12 associations out to 650 parsecs. But Gaia is just a whole different level in terms of precision, depth, and the sheer number of stars. It's revolutionized this field.
Well, this has been a fantastic deep dive. So just to sort of wrap up the main point, Gaia has really forced a major rethink about OB associations. We're
Yeah.
shifting away from that simple story of them being just extended versions of initially tight clusters.
That's the core message, yes.
Yeah.
The picture now leans much more towards them forming in situ, born relatively large and unbound within these complex hierarchical molecular clouds. There's likely some localized expansion happening within clumps inside them, but not a single grand expansion event dominating their formation.
It's quite surprising, isn't it, that these vast, seemingly expanding groups probably didn't start from one single compact explosive origin.
It really overturns a long-held piece of intuition about how these things work. The universe is often more complex and perhaps more interesting than our simplest models.
Absolutely. So here's something for you, our listener, to ponder. If these huge nurseries of massive stars, these OB associations, don't generally start as simple, expanding clusters, what does that tell us about the really fundamental physics driving star birth across the entire galaxy?
Yeah, and maybe what other assumptions we hold about how stellar nurseries work might need a second look now, in light of this more scale-free, hierarchical view. It suggests star formation might be a more continuous, less clustered or nothing process than we often assumed. Something to think about.